We're going to try to do this remotely today. So what I'm going to do is going to record a video just like we were having lecture time together. The main difference is going to be that you won't be able to ask questions live. But as we go through this, if you have any questions, feel free to email me about them or show up to the office, come by and see me. We're going to be in section 2.5 today. We're looking at continuity and the intermediate value theorem. This is the last bit of information that you need for your skills quiz and homework that's due this weekend. So let's take a look. First off, with a couple of definitions. We're going to start with the definition of continuity. We've seen this definition before. A function f of x is continuous at a point x equal to a if the limit as x goes to a of f of x equals f of a. Otherwise, we say the function is discontinuous at x equal to a. Now, the best way to think about this is we've already seen it once. In particular, this right here, which is part of the definition of continuity. This is the same thing as the direct substitution property that we discussed together in class last time we were face to face. If I can get it to snap, which it doesn't seem to want to do. There it goes. So this was the direct substitution property. Now, there are three parts to this definition. There are three things required in order for a function to be continuous at a point. And you may not see in that definition that there are three things, but in fact there are. So let's talk about the three things that are needed. First off, you need the limit as x goes to a of f of x to exist. Right? So you need to be able to calculate the limit at the point. That's the first thing. The second thing is the function value at the point needs to exist. So if you have the limit at a point and the function value at a point both existing, then continuity says they have to be the same thing. The limit has to point toward the function value. And so that's the actual definition, and the third part of this is this needs to equal that function value. Be prepared to give something back like this on the exam. The definition of continuity is a really important definition in all of the calculus sequence, not only Cal 1, but Cal 2 and Cal 3. Now, when we talk about continuity, we can also talk about continuity, since continuity involves the idea of a limit. We can talk about continuous from the left as being different than continuous from the right. The only distinction there is you're continuous from the right if the limit from the right matches the function value at that point. And you're continuous from the left if the limit from the left matches the function value at that point. Now, let's think about real quick what it takes to be continuous on an interval. So suppose I have an interval here, and we'll let it go from A up to B. And I have some function that I've defined on the interval. And I don't really care what the function looks like. Let's say it looks like that. What does it mean for that function to be continuous on that entire interval? Because if you look at our definitions thus far, our definitions are concerned with the limit at a single point. But here we have an infinity of points. Since it's a closed or open interval, in this case closed interval, we're going to include the endpoints. What does it take in order for there to be continuity on the interval? First off, the interval does have to be closed because we have to have closed circles at the end. Now, with that in mind, what does this say? Well, it says that the limit as we approach a from the right has to be equal to f at a. In other words, we have to be continuous at the left endpoint from the right. We have to be continuous at the right endpoint, so the limit as we approach b from the left needs to match f at b. So we need to be continuous at the right endpoint coming in from the left, and at every point in the middle, so every point between, the function is continuous. So it takes all three of those things in order for a function to be continuous on an interval. Now, let's look at some different types of discontinuities. We've already run into a couple of these in the course when looking at graphs of limits. Now we're going to look at them a little bit more closely, and I'm going to bring Desmos in here in a second. So let's talk about polynomials. We've already learned from the last lecture that every polynomial has the direct substitution property. So I will say, since all polynomials have the direct substitution property, then they have no points of discontinuity. There's not a single place on the graph of a polynomial where you have a discontinuity of any type. Now, that does not extend to when you have a piecewise function of polynomials like we'll see here. So let's take a look in Desmos. All right, so in Desmos, we're going to take a look at the function consisting of x squared for x less than 1 and 3 minus x for x greater than or equal to 1. Now, if you look at the graph of that function, what can you tell me about the kinds of discontinuities it has? Well, we'll start with x squared. X squared is a polynomial, so x squared has no discontinuities. There is nowhere on this red graph where the function is discontinuous. The same thing is true of the graph 3 minus x. The blue line, it is also a polynomial, so there are no places on the line where the graph is discontinuous. If there is a discontinuity, the only place it can occur, and this is true of all piecewise functions of polynomials, the only place where it can occur is at the place where the domain changes from one graph to the other, which in this case would be at x equal to 1. You can see that the limit from the left is 1 and the limit from the right is 2. They don't agree, so the limit at 1 doesn't exist, which means the function is discontinuous. Now, what kind of discontinuity do we have here? Well, we call it a jump discontinuity. So let's update our notes and we'll come back to that. So since the limit as x approaches 1 from the left of the function is equal to 1, and the limit as x goes to 1 from the right is equal to 2, these aren't the same value. This implies that we have what's called a jump discontinuity at the point x equal to 1. So this is our first discontinuity type. We're going to have a couple of these by the time we're done. Why is it called a jump discontinuity? Well, you can see in the graph the y value jumps up to a different y value or jumps down, depending on how you look at it. But the way to spot a jump discontinuity is your limit from the left and limit from the right at the point disagree. If you have a different value at the point, it's a jump discontinuity. Now, what I want to illustrate with the next example is that you can have an infinite number of jump discontinuities. So the next function here is x times if you look back at the notation real quick here in the notes, you've got this angle bracket underneath. So this notation is, in class, I would have asked anybody if they knew the notation. It's probably a new notation for a lot of you. It's called the floor of the function x, floor of x, which basically is the function which rounds down. So the floor of 2.2 is 2. The floor of 2.01 is also 2. The floor of 2.9 is 2. It always rounds down to the nearest integer value. In Desmos, we can just use the word floor to represent this. So x times the floor of x. Now you can see on the graph, there are a whole lot of these jumps. In fact, there are jumps at every integer. So you can see there's a jump at 1, there's a jump at 2, there's a jump at 3, and it just keeps going. Right? It kind of looks like a parabola. It kind of looks like x times x, but because of the rounding down, it creates these jumps. There's a jump at every single integer except at 0. All right. So there is a jump discontinuity at all integer values of x except x equal to 0. Now, these kinds of functions, these are oftentimes called step functions because they introduce several jumps within a function. Now, there's also something called the ceiling function, which the notation for ceiling is instead of having the bars come in at the bottom, they would come at the top. That function would round up. There's something called the greatest integer function. There's a lot of these kinds of step functions. These are actually prevalent in the real world. If you think about something like parking, they automatically jump up the price that you pay to park at some place as soon as you cross over a certain hour threshold, right? That's not a continuous change. It bumps up the cost immediately after passing a certain hour threshold. So we get those kinds of things in the world all the time when it comes to money situations, especially. So they're useful for modeling that type of thing. But the purpose of this example was to show you can have an infinite number of discontinuities. And so that's kind of the thing I want you to take away here. You can have an infinite number of discontinuities. This graph is an example of that. So that is allowed. It can be a bit much depending on the situation you're trying to analyze, but you can have an infinite number of discontinuities. Each of these were jumps though, so we haven't introduced a new type of discontinuity with that example. All right, the next function I want to look at is sine of 1 over x, and we actually saw this one earlier in the course when we were looking at squeeze theorem. So if I plot sine of 1 over x, if you recall, this is the function that oscillates infinitely often as we head towards 0. So the question for this guy is, what kind of discontinuity does this have? The reason it has a discontinuity is, remember, we established that the limit at 0 doesn't exist. The function value at 0 here also doesn't exist, so this is doubly bad. I will say that the limit as x goes to 0 of this function does not exist, and the function value at 0 does not exist. Now, those two things are features of what's called an infinitely oscillating discontinuity. So that's the type of discontinuity featured by this function. Infinitely oscillating discontinuity. All right, next one up. This is a rational function. Remember, rational functions, you've got to be careful about the denominator. If I have x equal to -2 in the denominator, it could create a vertical asymptote, except it actually doesn't here. If you look at the limit as x approaches -2 here, we've worked problems like this before. This is the same thing as x plus 2 over x minus 2 in the top when you factor it. And when you cancel, you're just left with x minus 2, which if you evaluate at the limit now becomes -2 minus 2 or -4. So the limit at -2 is -4, but the function value at -2 does not exist. Why does the function value not exist? Well, here's the function. Can you plug -2 into this function? No, you cannot. You'll be dividing by 0. But you still have a limit because this is actually a 0 over 0 type. So the possibility of a limit remains. These are very common discontinuity types. In fact, most of the problems that we did by hand when we were solving limit problems had this type of discontinuity. It's where the limit exists, but the function value does not. The function value has been removed where it's supposed to be. We call these removable discontinuities. All right, what's the difference between this rational function and this one? Well, as far as discontinuities are concerned, it's actually a big difference. 1 over x minus 3, if I take the limit as x goes to 3 of this graph, I'm going to get a couple of different answers here. I'm going to get infinity if x is greater than 3. In other words, if we approach 3 from the right. So I'll say we get infinity if x approaches 3 from the right. And we'll actually get negative infinity if x approaches 3 from the left. But what's actually happening here is at 3, we have a vertical asymptote. And you'll see in the graph here in a second, we actually go down to negative infinity as we approach from the left. We'll talk more about vertical asymptotes in the next lecture. We actually go up to infinity if we approach from the right. So this is a infinite discontinuity is what we call these. Not to be confused with infinitely oscillating discontinuity, but infinite, if you want to say asymptote discontinuity. So we call it an infinite discontinuity. It creates a vertical asymptote at the point. So let's jump back into Desmos real quick and talk about these last two rational functions. So we'll start with the one that had the removable singularity. It was x squared minus 4 over x plus 2. And the interesting part of this graph certainly is what's happening at -2. So let's come over here, show -2. I'll plug in a point at -2, f of -2, and label that. You can see that it doesn't want to show up, and that's because f of -2 is undefined. We calculated together that the limit there should be -4. So I'll put in -4 instead. But here's the problem. Even though Desmos is showing this with a darkened in circle, the function value is not there. So I'm going to use an open circle instead, because technically that's what the graph of this function looks like. It looks like the graph of x minus 2, which is what you get when you simplify this, except it's missing the value here. And you can see, if I drag and hold along the line, I've got values everywhere, except if I stop exactly on -2, Desmos says it's undefined. So this is what the graph of this looks like, and if you have a hole in a graph like this and the function is nowhere to be found, the limit from the left matches the limit from the right. This is a removable singularity. The other one that we just looked at was 1 over x minus 3. So this is the one that had the vertical asymptote. I can go ahead and put in the asymptote at x equals 3. And here you can see the limit from the left is negative infinity, the limit from the right is positive infinity. We'll talk about how to find those limits in the next section. But for now, I just want you to know that this type of behavior, this vertical asymptote behavior, is a discontinuity. It's a discontinuity because the limit doesn't exist at that point and the function value doesn't exist at that point because both are infinite. So we call these infinite discontinuities. The last one that's on our list in the lecture notes is the tangent function. It's a function you should all be familiar with. And the purpose of me showing you this graph is to show you that it is possible to have an infinite number of these infinite discontinuities or vertical asymptotes. The function tangent, if you will recall, is defined as sine divided by cosine. So when we look at tangent of x is sine divided by cosine. That means that anywhere cosine is 0, which would be, cosine would be 0 at pi halves, 3 pi halves, etc. So this is, I'll just write it this way, plus or minus pi halves, plus or minus 3 pi halves, plus or minus 5 pi halves, all the odd multiples of pi halves. These are all vertical asymptotes. So this is an example of a problem that has an infinite number of asymptotes. Now, if you're keeping track of the highlighted things here, there are in fact 4 different discontinuity types in this course. There are actually more than 4 types, but for this course, these are the 4 that we'll see. They are a jump discontinuity, very common. A infinitely oscillating discontinuity, not very common, and also not extremely important. A removable discontinuity, extremely important, happens all the time in the problems we work out by hand. And asymptotes, which we'll see all throughout the course. So those are the 4 types of discontinuities that we'll encounter in the course. So I want to give you a moment here to look at this graph. Sorry, it's a little bit grainy because the image is blown up here. But I want you to look at this graph and tell me all of the values at which the function is discontinuous. So pause the video, write down the list of where you think discontinuities occur and what types of discontinuities you think they are. So I'll give you a second to do that. All right, if you haven't paused the video, go ahead and do so. I'm going to talk about the answer. At -3, so at x equal to -3, you have a removable discontinuity. At x equal to 0, you have a jump discontinuity. At x equal to 2, now this is the one that may be tricky for some of you. If you look at what happens at x equal to 2 and how it's different than the jump, remember a jump happens when the limit from the left does not match the limit from the right. We get a jump. But here, the limit from the left and the limit from the right are both pointing toward this open circle. It's just the function value has been removed elsewhere. So this is actually a removable discontinuity, like the one at x equal to -3. Removable discontinuities come in 2 flavors. The first flavor is where the limit exists at the point, but the point is just altogether missing. The second type is where the limit exists at the point, but the function value is somewhere else. It is defined, but it's just not where it should be. What about at 5? Well, one of the things that people will often teach for the definition of discontinuity is what's called the tracing property, meaning that a point is continuous if you can trace through the graph of that point. So if you think about applying that property to 5, I can trace through the value at 5 without having to lift my pencil. So that value is actually okay when it comes to continuity. We will not lose continuity at such a point. These are called corner points. We'll talk later about what does happen there. There are some bad things that go on at those kinds of points, but you do not lose continuity at those points. Finally, you can see here at x equal to 6, we have an infinite discontinuity in the form of a vertical asymptote. All right, so being able to recognize and name the different kinds of discontinuities that we encounter in the course, important property to be aware of. All right, you're going to have a couple of problems like this on your homework, and I think at least one on your skills quiz. Let me show you the idea behind this problem in Desmos, and then I'll show you how to solve for it by hand. So this is a piecewise function. The top piece is 2x plus 8m. And this is for x less than or equal to negative 2. And I'm going to add in a slider for m because we're going to want to change the value of m. The middle function is mx plus k. I'm going to add in a slider for k because we're going to change its value. And the bottom function is negative 3x squared plus 8x minus 2k. And that one is valid for x greater than 2. The middle one is valid for negative 2 less than x less than or equal to 2. All right, so what you can see here is we've got 3 different graphs. And if m were 0.8 and k were 1, the graphs are definitely discontinuous, right? There's jumps at negative 2 and positive 2. Now, each graph is a polynomial, right? So we know that there are no discontinuities on the graphs themselves. It's just where they switch from one graph to another, which would be at negative 2 and again at 2. So looking at this, the whole goal of this is for us to be able to solve for the special value of m and k that will make these continuous. So you can see here as I move k around, maybe I can get it to match up over here, but if it matches up over here, then the purple and the red don't match up anymore. So is there some sort of value on this side that I can get things to match up with? The point is, we could sit here and play trial and error all day long and may never actually get the right value. So how do we actually find the correct value? Well, finding the correct value, we're going to do that by hand. So if you come back to this example, the whole point here is I need the limit from the left and the limit from the right at each of these values to match up. So let's start with negative 2. So at x equal to negative 2, continuity says I need the function value at negative 2 to equal, and I'm going to introduce a new notation here just to make this a little bit more efficient. The function value as we approach negative 2 from the left should equal the function value as we approach negative 2 from the right. Now, these are limit calculations that I'm doing, but I'm also talking about the function value at those points, because remember we want continuity, so continuity requires limit and function to match up. So this is a very common shorthand notation for this. Let's think about the thing on the left. This is the function's value at negative 2 to the left of negative 2. So if we're to the left of negative 2, we're on this graph. And if x is negative 2, then you get 2 times negative 2 plus 8m. That has to equal, if we're to the right of negative 2, we're on this graph. So if x is negative 2 plugged into this graph, that would be negative 2m plus k. If I do a little bit of work on this, this is 10m, bring the 2m over. And then this is, I'm going to bring the k over, that'll be minus k. And then on the right-hand side, you've got negative 4 right here, but if I bring it over, it'll be a positive 4. So this is the condition on the left-hand side. So this is at negative 2. At 2, the condition is similar. I need the function value at 2 from the left to equal the function value at 2 from the right. So the function to the left, to the right, excuse me, of negative 2 would be, or no, excuse me, the function to the left of 2 would be this middle one. So that's 2m plus k. And the function to the right of 2 would be this one. That has to equal negative 3, 2 squared plus 8 times 2 minus 2k. So that's 2m plus k, 4, negative 12 plus 16, that's 4. And so writing it like I wrote this one over here, this will be 2m plus 3k equal 4, I believe. Let me make sure I did that correctly. 2 squared is 4. Negative 3 is negative 12 plus 16. Yeah, looks good. Okay, so we have two equations now that have to be satisfied. Well, this is taking you back to Algebra 2 in high school. How do you solve a system of two equations with two unknowns? So this would be 10m minus k equal 4, and 2m plus 3k equal 4 as well. There are many different ways that I could explain how to do this, and it really just depends probably on how you were taught, but I was taught that you want to create a cancellation here. So you see the 3k here and the minus k here. If I multiply this equation through by 3, I can get a negative 3k, which when added to this will cause it to disappear. So that's what I'm going to do. Multiply the top equation by 3, and then add both equations together. If I do that, 3 times 10 plus 2 is 32m. 3 times negative k is negative 3k, plus 3k is 0k, which is the point here. And 3 times 4, don't forget about the right-hand side. 3 times 4 is 12, plus 4 is 16. So you see how that isolates m. I can now solve for m. It's 16/32, or 1/2. Now, once I have that value of m, I'm free to plug back into either of these two equations to get k. For instance, if I make m 1/2 right here, you get 1/2 of 10, which is 5. 5 minus k is 4. That forces k to be 1. So lots of different ways to go about actually solving for those, but those are the two values that work. Let's check and make sure that they work. So we said that if m is 1/2 and k is 1, things work out, and wouldn't you know it, we're correct. You can see here that there's no gap. There are corners here, but there's no gap here, right? We can zoom in. We have successfully bridged the two functions. So this is actually a really important mathematical skill, the ability to create a kind of intermediate function between two other functions to bridge the gap. We'll talk a little bit more about this later in the course, but this has kind of far-reaching applications in a variety of fields. But it's this idea of continuity and eventually making these transitions smooth between the points. All right. So that brings us to the last thing I want to discuss, which is the first of 3 important theorems in the course called value theorems. This is called the IVT, or intermediate value theorem. Basically, you can think of this theorem as the consequence of continuity. So my remarks about this theorem are the IVT shows the consequence of a function being continuous. In other words, what can we count on when we know a function is continuous? Well, if you read the theorem, it says, suppose you have a function on an interval from a to b. And the endpoints of the function don't have to be the same. In fact, they shouldn't be the same, or else this is kind of boring. But suppose I have a function that starts here, and it doesn't matter where it ends, but I'll just make it a different ending point than the starting point. It ends there. And what this theorem says is if I know the graph of this function is continuous, then as I draw in the graph, whatever it looks like, and connect these 2 points, pick any value between the starting y value and the ending value. Pick any value. Call it n. So that creates kind of this imaginary line through the problem. The theorem says if this function is continuous, then there's no way you don't intersect this line. You have to. So it doesn't matter how I draw this, I have to, and I may intersect it multiple times, I have to intersect this value at least once. This theorem says that all values between your starting point and ending point, y values, of a continuous function get hit. These are called the intermediate values. Every single one of these values is hit by the function at some point. And where it hits, the function calls that the value c, and you'll note that at c, the function value is in this intermediate value that's spelled out. So that's what the theorem says. The theorem actually has a really nice application in the proof of many things that may seem counterintuitive or even odd at first, and I wanted to give you an example of one of those. So this is called the hiker's paradox. Suppose a hiker begins heading up a mountain at 6 a.m. on Saturday morning, and they arrive at the base camp by 6 p.m. that evening. The next day, they return on the same trail. They leave at 6 a.m. from the top of the mountain, and they arrive at 6 p.m. at the bottom of the mountain. So here's the question that I want to ask, and I want you to commit to an answer in your mind before you see me kind of move on to the next part of this. Is there some place on the trail that the hiker visited at the exact same time of the day, both coming and going? So let me rephrase this slightly. Is it possible that if I don't tell you how fast you have to go along this trail, that if you take the exact same trail up as you took down, although you can go at different speeds both days, does there have to be some place on both days you were at the exact same place at the exact same time? So I want you to think about that. And then once you commit to an answer, you can pause the video, try to think about it, commit to an answer, and then see what the answer in fact is. Okay, turns out the word paradox might have spoiled it for you a little bit, because even though it's hard to imagine that that statement is a true statement, it is indeed true. There must be some place on the uphill ascent and downhill descent along that trail where we were at the exact same time and same place on both days. Let me explain it with a graph. So let's let the axis along the bottom be time in hours. And we'll go all the way up to 6 p.m., which would be t equal to 12. And we're starting each day at time 0, which would be 6 a.m. Now, let's suppose that on the way up, this is our base camp. So before, the vertical axis here, by the way, is, I'll call it elevation. So this is our elevation along the trail. So you imagine the base camp has some sort of, static elevation here. That's what we start our day off at. Now, what happens over the course of the first day? Well, over the course of the first day, you're going to climb the mountain, which means your elevation is going to go up. You're going to stay on the trail, and you're going to end at what I'll call summit camp, which is going to be at a higher elevation up the mountain. Okay, so summit camp, you're not going to get there on the first day until over here at 6 p.m. So I got to draw some graph that basically goes over to here, the summit camp elevation at 6 p.m. I don't care what graph you draw. You can draw anything you want, right? So maybe, probably not a straight line. You can draw any graph you want. So maybe that is an elevation graph of our path along the trail. So as we're following the trail of the mountain, this is how our elevation is changing. Now, there's one thing I want to talk about the graph that you drew. Your graph can look like anything. In fact, your trail could come up above the summit and then come back down to it, whatever. It has to be continuous. Why does your graph have to be continuous? Well, as you're walking along the trail, you cannot skip over any elevation values. Even if you were to fall off a cliff, you would hit every single elevation on the way down. We cannot teleport, so human motion is continuous. We must cover every elevation marker between the base camp and the summit camp on our way to the top. Now, this is what I will call UT for the uphill ascent function. Now, the reason that this paradox is true is consider what happens on day 2. At day 2, you're at the summit camp at 6 a.m. and you have to make your way down the mountain to get to base camp elevation by 6 p.m., 12 hours later. If you've already drawn in your uphill graph, there is no way to draw in a graph that goes from here to here without crossing the graph you've already drawn somewhere. It's just not possible. So connect these 2 points without crossing this graph somehow. You can't do it. So maybe this is downhill. So I'll call that D of T. This is my downhill descent. And you'll note that no matter how I drew the 2 graphs, there must be some point like this. And at that point, what can you tell me? Well, you can tell me I'm at the same elevation at the same time on both days. So this point proves the paradox is true. So, this is an example of where intermediate value theorem is helpful because you know you have to pass through every point. It's a consequence of the function being continuous. We'll make some similar arguments to this one later in the course. But for now, I just want you to memorize and understand the intermediate value theorem that we've introduced here. All right, that is the end of the material out of section 2.5. So you should be perfectly situated at this point to finish Skills Quiz 2, which I believe is due on Friday night, and then homework 2, which I believe is due on Sunday night. Stay warm, be safe. I'll see you back in class, hopefully, on Friday. But until then, watch this video. If you have any questions, let me know.